It's really a pleasure to be invited in this remade seminar, or actually webinar. So I think this is my first talk that is then available on YouTube. So also quite exciting for me. My name is Lucas. As said, I'm working in Munich at the neutron research reactor there called FRM2. I'm working at the Heinz Maier-Leibnitz Zentrum, the MSZ there. And I'm an instrument scientist. And together with my colleague, Johanna, I'm responsible for a neutron spin echo instrument called Reseda there. And as already said, so today it's about polymer films. These films are based on cellulose on the one hand, but they are also electrically conductive. So we also have a conductive part in there. And this is a project that has been going on now for a couple of years between me and the Munich side and the groups of Daniel Söderberg and Stefan Roth at KTH in Stockholm and the German electron synchrotron DESY in Hamburg. And the overall idea is to investigate structural and dynamical properties of these films. Neutron will play a big role in this, and to link then these information which are on the nanoscale to the macroscopic world, to macroscopic functionality, and in our case, or for this talk, it will be the electrical conductivity. Now let's jump directly into the topic. So I said these films are based on multiple components. Now in this case, it's two. The first component would be PEDOT PSS. You see the chemical structure here on the left. This is the conductive part. So it's a conductive and water-soluble polymer blend. It's a model system. It's very well understood. It's really nice. It's increasingly applied as an organic electronics. So you can build a battery cathode, for example, out of it, or a super-capacitor or electric circuits. Something like this can deposit very thin layers, very flexible layers. This is all great, but it also comes with one drawback. If you expose it to a humid environment, it takes up quite a significant amount of water, as you can see here on the right. So this is the water content that is inside the films as a function of time and as a function of relative humidity. And these films really absorb water quite quickly, so it's a matter of minutes. And already at intermediate humidity levels, so 40, 50%, we have 20, 25 volume percentage of water inside these films. And it gets increasingly worse when you go to high humidity levels. Now, water inside these films lead to a swelling mechanism, structural rearrangements, certain aging, degradation mechanisms, so long-term stability is not very good. And eventually you have a loss in performance. And here the performance is the electrical conductivity. So these films degrade after some time. And this is, of course, something we don't want to have. And an idea we had to overcome this is to blend it together with cellulose. And we use a special type of cellulose, cellulose nanofibrils, now abbreviated with CNF. These are fibers, basically, very long in the micrometer range, but very thin, so 5 to 10 nanometer. So that's why we call them nanofibrils. And these fibers are known to really enhance the mechanical integrity and to limit water absorption of a polymer film, for example, of a PEDOT PSS film, while at the same time keeping all the good stuff like flexibility, lightweight, mechanical stiffness, and so on. And now if you are a scientist, a material scientist, or a scatterer, or a physicist, chemist, you have immediately a lot of questions in mind when blending two materials together. One of the material is a blend itself, and the other material is a highly hierarchical material. There are some questions, and for the sake of time, I made a collection of 3 questions for this talk, which can also be seen as kind of an outline throughout this presentation. Question number 1, the composite films, do they still absorb water? And if yes, do they still swell? Question number 2, if there is water, where does the water actually go? How does it move in the film? How does it interact with our film? So especially water-cellulose interaction is a long-standing challenge to resolve these interactions in the wood science community. So we're definitely interested in this. And question number 3, this would be then the link to the structure, so what is actually the water doing to the film nanomorphology, and then the bridge to the macroscopic world. What is the influence then, of course, on the electrical conductivity, because we want to build a macroscopic device or application out of it. Now, before we can tackle these questions, we need to prepare our films. And this we can do with a technique called spray coating. A former PhD student at KTH, his name is Calvin. He developed this spray coating setup where you simply mix PEDOT, PSS, and CNF together with a ratio of 1:1 in an aqueous solution, so everything is water-based. That's quite nice. And then you have a certain spray coating protocol. So you have certain amount of, or a certain time interval of spray pulses and a certain time interval of drying. And typically we spray coat on a heated substrate, a silicon substrate that is heated to 120 degrees. So the drying of aqueous solution is quite, happens quite quickly. And the nice thing of this technique is then that you can spray coat very thin films like these. So around 20 nanometers on a silicon substrate. They are macroscopic in size. So 10 centimeters in length. The width is around 2 to 3 centimeters. Or if you are willing to invest a little bit more time and material, of course, you can also spray coat thicker films. So these are around 10 microns. And you can even detach them from the silicon substrate once you cross a critical film thickness. I am not sure about the film thickness, but once they are thick enough, you can detach them from the substrate, and then you end up with these freestanding PEDOT, PSS, CNF films. Also macroscopic in size. I think the length here would be around 7 centimeters, but on a nanoscale, still homogeneously mixed. So here you see an AFM image of these smaller films or thinner films. You see here these fibrils, and the PEDOT, PSS are then dissolved in between. So very nice technique to prepare thinner or thicker films. So an easy upscaling, let's say in all 3 dimensions, although easy would be in quotation marks because it takes a little bit of time. So these thicker films, it takes hours, I would say, until these films are prepared. And then we want to tackle already the first question. So do these films absorb water, and do these films swell? And this we can answer with a technique that is called neutron reflectometry. And just very briefly, the background of this technique, how does it work? You have a neutron, obviously. It impinges on your sample. It interacts with your sample, either gets reflected or it penetrates the film. The film is here indicated with this layer stack, just to mimic potential gradients within your film in vertical direction. Then you have an outgoing or scattered neutron. You have the 2 wave vectors, the incoming and the outgoing neutron. And the subtraction gives you the momentum transfer Q. And this Q is only in Z direction. So you get only information in vertical film direction. That's why we name it QZ. And the typical reflection curve would look like this. So you would have the intensity as a function of QZ, momentum transfer. And there are 2 important features. The first feature, here it's barely visible. Apologies for this, but this is the critical edge. So this is at very low Q values. You have a certain region where you have total reflection. So there the neutron is not able to penetrate the film, and all of the neutrons get reflected. This is called then total reflection. And then at some Q, Z value, neutrons penetrate the film, and then you get this shape, very characteristic shape, with these fringes here. They are called Kiesig fringes. And they are dependent strongly, for example, on the film thickness. So if you increase the thickness, these fringes move closer together. And this is how you get information about the film thickness, for example. Another information we extract is the SLD. SLD stands for scattering length density. It's a measure how strongly your film interacts with the incoming neutrons. An increase in SLD leads in particular to an increase of this total reflection. So this critical edge here, once the neutrons are able to penetrate the film, is shifted to higher QZ values, while also these fringes are more pronounced even at the high QZ range. And a third information we extract would be the roughness. So the rougher the film, the stronger the dampening of these fringes. And this is also one of the prerequisites of these films. If you want to do neutron reflectometry, they have to be reasonably smooth in order to get reflectivity curves that you still can analyze. Analysis of these films simply works by fitting them. You can apply a layer model similar to these. To this deck here, you can add, of course, a couple of more layers. I said to simulate gradients or anything in there. And then you get information about film thickness, SLD, and the roughness, not only of the entire stack, but also of your individual layers. And as a bonus, so to say, you can also transform this into an SLD profile, and this I will show you on the next slide. So this is just the basic of neutron reflectometry. If there's still any question, we for sure can address these then in the discussion part. Now, these are the reflectivity curves of our material, of the PEDOT PSS CNF films. Intensity is a function of QZ. They do not look so nice than the simulated curves on the last slide. Real science rarely does, but we can analyze them. So we have 4 of them, 2 black ones, 2 blue ones. The black ones correspond to the films in low humidity and the blue ones in high humidity conditions. So we have 2 cycles of exposing them to low and to high humidity. And the red dashed lines is the fit, where we apply this layer model. Now we extract an SLD profile, SLD as a function of the film thickness, set SLD, scattering length density. You would have here the substrate and then on top the film, and at some point the film air interface, polymer air interface. And what you see immediately is that we definitely have changes in the thin film structure, vertical thin film structure, so QZ. From black to blue or from low to high humidity, something is happening. The SLD is increasing. And we address this to an absorption of water. In this case, we use D2O, so heavy water, because it has a very high SLD. It gives us a better scattering contrast. And this increase in SLD is D2O moving into the film. And this happens especially close to the substrate, because here the difference in SLD is the highest, and then it somehow fades out. This is the first thing. Another thing we see is that the film thickness actually remains more or less constant in a dry and in a humid environment. And this was really surprising because we measured the pure PEDOT PSS films a couple of years earlier, and there you see a massive swelling. So swelling factor of 2.5 or even more from the dry to the humid PEDOT PSS film. So we have an absorption of water, yes, but we don't see a swelling, which can directly be related to the blending with CNF. But now that we have water in there, we want to know what is actually water doing there. What is the role of water? What is the dynamics of water? How does it move? And this is something we can address with another neutron technique. And this is called QENS, quasi-elastic neutron scattering. So in general, a scattering event can be elastic, meaning you don't have an energy transfer. It can be inelastic, meaning you have an energy transfer, or quasi-elastic, meaning you have an energy transfer, but a very small one. And we are interested in this third case, the quasi-elastic case. Now, just generally how QENS would work. Again, you have an incoming neutron, which is interacting with your sample. It gets scattered. And by having the incoming and the outgoing neutron wave vector, you subtract them, just like we did with the reflectometry, you get the scattering vector Q, which tells you something about the length scale. But you can measure a second thing. If you know the wavelength of your incoming neutron, and then you measure the time of flight from of the neutron that it takes from the sample, the scattering event, to the detector, then you know if there was any energy transfer occurring at the sample. And if it's in this quasi-elastic range, then we would be interested in this. So basically, QENS is counting the number of scattered neutrons as a function of energy transfer. This is measured by the time of flight, and the scattering vector Q. This is measured by these neutron wave vectors. And this also means that Quenz is sensitive to both a time and a length scale. So time scale meaning how fast are things moving inside your material, your sample, you get out of the energy transfer, and the length scale information you get out of the scattering vector Q. And this is a really great advantage of this technique. Now, typical Quenz spectrum would look like this. You have the intensity as a function of energy transfer, and this spectrum or this data is comprised of two things. So first, the elastic line here shown in red. This is so in a perfect experiment, in a perfect instrument, this would be just a line, the elastic line. But you all know science isn't perfect. Instruments are not perfect, so we have a certain resolution, and this would be the resolution limit of the instrument, the broadening of this elastic line. And then there's the quasi-elastic signal, where we would then detect the quasi-elastic scattering signal, where the quasi-elastic energy transfers are happening. And now one more detail, and then I'm done with the theory part of this technique. With Quenz, we detect foremost the incoherent scattering, and hydrogen is an element that has an incredibly high incoherent scattering cross-section. So whenever you have hydrogen in your sample, your signal would be dominated by the scattering signal coming from the hydrogen. Hydrogen is also in water, and we are interested in this water. So if you set the Quenz instrument to a suited energy range where you would detect movements of hydrogen, then you would detect only the movement of hydrogen that sits in water molecules. So then you can really follow along the movements of water. And this is exactly what we did at the IN5 instrument at ILL, where we were interested then in the water dynamics. How does water move in our PEDOT PSS CNF films? And in this case, we took these freestanding films. For this experiment, that really came in quite handy, because we took these standard aluminum cylinder cells from IN5. That's basically an inner cylinder in an outer cylinder. And in the inner cylinder, we rolled around these PEDOT PSS CNF films and then put it all in the outer cylinder, closed it, and we were ready to measure. And by rolling this around the inner cylinder, we increased the scattering volume. And it's a very elegant way to still be able to measure relatively thin films. So for a thin film physicist, 10 microns, which is the thickness of these films, is not thin. But this is somehow a compromise of having a reasonable scattering volume, meaning reasonable measurement times, but still also reasonably thin films, even though they are in a micrometer range. For the protocol, the measurement protocol, here we have now 3 cycles of exposing them to low and to high humidity. So we dried them simply by a nitrogen flow, then closed the cell and measured it. It was the dry measurement. And for the humid ones, we injected 20 microliters of water into these cells, let them equilibrate for a couple of hours, and measured them then at this EN5 instrument. And this is now our data. So this is called a dynamic structure factor as a function of the energy transfer. In this case, it's only the very first cycle. So we have a dry film, we have a humid film, and we have in blue pure water vapor as a reference or an empty cell measurement. You already see some differences, so something is happening there. That's always great to see when you are at the beam time and you see changes, then you know, okay, something's happening there. And we can do a little trick to make these changes a bit more visible. We can transform this dynamic structure factor into the dynamic part of the susceptibility. Now, susceptibility means, or susceptibility measures how a system or films respond to an external perturbation. In this case, the external perturbation would be the scattering event with a neutron. And then you have the susceptibility as a function of frequency. So frequency is just another energy scale. And it's a very convenient way of plotting or aligning the different dynamical contributions of water, because water is what we see. We set the energy range so that we follow along the water movement. And what do I mean with different dynamical contributions? So for pure water, we would have three. We have the diffusion, labeled with D, simply water molecule moving from A to B. Then we have another contribution at higher frequencies, meaning they are a little bit faster, these movements, denoted with L. This corresponds to a so-called local effective motion. These are movements on a local scale, faster than diffusion, but still slower than vibration, which come at very high frequencies, so water vibrations. So this is only pure water, and if you now put this water molecule into a polymer film, the situation gets even more complex. Namely, it's this graph, this curve here. So again, we see these three contributions: the diffusion, this effect, this local motions, and the vibrations. But we have two more peaks coming up. A very prominent peak at very low frequencies, meaning very, very slow movements. And these are all the movements that come from the polymer side chains, backbone movements, and so on. Because there are also hydrogen atoms in there, of course. But as said, the energy range is set so that we only follow the water molecules, and these movements are actually beyond the resolution limit. So this is modeled simply with the resolution function of our instrument. And we don't take this into account for the analysis. And then we see a second peak appearing, also at low frequencies, meaning slower than the diffusion of water. And this we also address to diffusion of water, but of a different kind of water. So we actually have two water kinds in these films. Let's call the one type bulk water, even though technically bulk water, well, water in a film is not bulk water, but for the sake of clarity, let's call it like this, which is surrounded only by other water molecules and is far away from the polymers. And we have hydration water, which sits in the hydration shell of the polymers, very close to the polymers, tightly bound, and therefore it's moving on a different time scale. It's moving slower, and therefore appearing here at lower frequencies. So two types of waters with different motions. If we now dry the film, some of the peaks disappear. We don't see the diffusion of this bulk water kind anymore, and this local effect is also disappearing, or at least becomes so small that we would not need to model this curve anymore. And we are left with the diffusion of hydration water and still these vibrations. So now, to us, this means that when you dry the film, bulk water is completely removed from the film. All of the bulk water is pushed out, but there's still water left in the film. But this is present as hydration water close to the polymer chains, but to a lower, but to a smaller part. So the amplitude of this peak decreases when you dry the film. So very complicated slide with a lot of information, but if you take away 2 points, I'm already happy. So the first one would be this transformation to the susceptibility allows you very transparent separation of the different water dynamics. And we have two water species present, bulk and hydration water. And now we can take these two water species, water kinds, and plot the ratio of these as a function of the relative humidity. And this is what I've done here. So here you see the relative water population, hydration and bulk water as a function of relative humidity. And here you see two things. The first thing is that we always have more hydration water as compared to bulk water, even in the humid state. And I think this is a result of having these CNF, these fibrils present in there. It really gives you a cellulose-based scaffold, which holds everything in place while still being reasonably flexible. And you don't have too big voids or pores that can be filled with water and then start to swell, because these films also don't swell. The CNF, everything holds in place. So there's actually not so much space for bulk water, and it's present in this film, yes, but to a relatively low amount. And most of the water is present here as hydration water close to the polymers. And the second thing is that the first cycle of low and high humidity somehow differs from the remaining two cycles. So we start with a relatively high hydration water fraction, which then decreases in the second and in the third dry state. And the differences get even more pronounced in the humid state. We have much higher hydration water fraction as compared to the other two humid states, but a lower bulk water fraction. So something is happening there. And now another thing, we can go even further in detail in the analysis of this data. For the different water species, we can assign different diffusion coefficients. So we get a diffusion coefficient for bulk and hydration water, and we see that this diffusion coefficient is actually changing when the amount of the respective water species is changing. So it's dependent on the actual amount that is present in the film, which is somehow cool. So for hydration water, if you have in the dry states, you have a low amount of hydration water, meaning hydration shell is not so prominently occupied. So there is a lot of free space, I would say. So the interaction with the polymers is strong, very attractive, which speeds down the water molecules. In the humid states, hydration shell is larger. The interactions of the individual water molecules to the cellulose, the PEDOT weakens, and we have an accelerated diffusion. So this would be my interpretation of this changing diffusion coefficient of the hydration water. For the bulk water, this is still under discussion in our groups, why this is decreasing, why diffusion slows down when you have actually a higher amount of bulk water. We're still trying to figure this out. If you have a clever idea, we should talk. But yeah, so diffusion behavior is also dependent on the amount of water that is present in these films. So we have a pretty good idea what is actually happening in these films. And now comes the last part. Now we want to correlate this to the nanomorphology. And this we can do with another neutron technique, small angle neutron scattering, which you usually measure in transmission mode. But if you have a very thin film and you don't have a lot of scattering volume, you do a little trick and rotate it by 90 degrees and illuminate the film under a grazing incidence, then you have a certain footprint and a larger illuminated area, and you get a better signal, better statistics. But then also your scattering image looks different. For example, like this. And what you can do now is you can, for example, do a horizontal line cut at a fixed QY. Or this is a vertical line cut, sorry, at a fixed QY position, which, for example, looks like this. It has one prominent feature that is called the Yoneda peak. This is at a QZ position that is slightly above the total reflection. So we are just at the right angle that the first neutrons can penetrate the film. Then you have a certain effect of an evanescent wave underneath the film surface. And this leads to an amplification of your scattering signal. And this is then called the Yoneda peak. But if you do, and then what you can do then is, for example, a horizontal line cut, for example, at this Yoneda position, because there you have a lot of signal, which would look like this. And this you can then fit with certain structure factors, form factors, which give you information about the size, the shape, and the distance of characteristic periodically appearing features in your film. Just if you do this at the Yoneda position, keep in mind that you are rather surface sensitive. If you want to be more bulk sensitive or extract the morphology from the bulk of the film, then you can go to higher QZ values where you are more bulk sensitive. But with these vertical and horizontal line cuts, you get then morphological correlation perpendicular and lateral to the surface, to the substrate or the film surface. And this is what we also did with our films. So once again, we have 3 cycles of low and high humidity. And this is the 2D scattering images already in Q space. So we have QZ and QY. And from this, with the analysis I just showed on the last slide, we can then extract a morphological model, which I briefly want to show you here. So basically, we have 3 different components. We have these red spheres indicating PEDOT PSS rich domains. We have these brownish bars. These are the cellulose fibrils. And then we have these cloudy things. This is water. We start at the initially dry state, and you see these CNF fibrils, the nanofibrils. And if you look very, very closely, maybe on the screen it works. If I give a real talk with the beamer, it's always hard to see. But these bars are reddish. So they are actually red on the surface. And this means that PEDOT PSS has wetted these fibrils. This we measured with complementary technique. And in between, you still have these PEDOT PSS rich domains. Now, when you humidify the entire system, water moves into the film. We saw this with Quenz, we saw this with reflectometry. And what we see here is that PEDOT PSS dewets from the CNFs and forms smaller clusters along these fibrils. And in between, still we have these PEDOT PSS rich domains. Now, if we dry the entire system, interestingly, we don't go back to this first state, but we enter a third state, namely this state here. Basically, Giesens gives us a very detailed structural model in lateral direction. And what we see here is that we have quite significant structural rearrangements that are partially irreversible. So after a first humidification step, we enter a different morphological loop. So something happens during this first humidification step. And this is something we also saw with the Quenz data, where the first cycle somehow differs from the subsequent 2 cycles. So I draw here a line, and here we could draw the line after or just before the first humidification step. And this is a very nice correlation between the water dynamics and the nanomorphology of our material. And now it's time to bridge these properties to a macroscopic functionality. And in our case, it's the conductivity, which is shown here in blue. So the gray and the red bars are not important for this bar. Please focus only on the blue bars. In the very first initially dry state, we have the highest conductivity. And this corresponds to this nanomorphology. This corresponds to this ratio of hydration and bulk water. If we humidify the system, the conductivity decreases. We are in this state. We are in this water ratio. This drop in conductivity we address to the dewetting of the PEDOT PSS. Once we dry the system, PEDOT PSS rewets on the cellulose fibrils, and the conductivity increases again, but it never reaches this initially highest state. So we never go back to this initially dry morphology or this ratio of hydration water, but we go to something else, which corresponds to, let's say, an intermediate conductivity. So it's a very nice correlation, not only between dynamics and structure, but also to a macroscopic functionality. And now, of course, the question would be, is it possible to go back to this state of hydration and bulk water ratio corresponding to this morphology, corresponding to this optimized conductivity? Or is there even a further point where we can further optimize the conductivity? And this would be kind of an outlook for future studies. And funnily, I'm currently at ILL and measuring exactly this. So maybe then at some point there's a future remade webinar where I can tell you more about this. And with this, I want to summarize the talk. So I asked a couple of questions in the beginning. Do the composite films absorb water? Clearly, yes, but they don't swell. We have a pretty good idea where the water goes. It's mainly present there as hydration water, not so much as bulk water. We also know in quite some detail how these water species move. Diffusion coefficient is dependent on the amount of water that is actually present. And I also talked on the last two slides about the impact on the film morphology and the electrical conductivity. So a de-wetting of the PEDOT PSS in a humid state leads to a decrease in conductivity, and a re-wetting in the dry state leads to an increase in conductivity. And the question now is there a certain sweet spot where we can have an optimized conductivity? And if I have just 2 or 3 more minutes, I would like to show you one other thing, which I think is very, very cool. I talked a lot about QENS and the advantages of QENS, but one thing QENS cannot do, and this is distinguishing between a water molecule if it's sitting close to a PEDOT PSS chain or close to a CNF chain. This QENS cannot do, but there's another technique called Raman spectroscopy, which measures more the polymers. So it measures or it probes the functional groups, the vibrational energies of functional polymer groups, and these change with hydration. So there we could actually distinguish between the different polymers, and that's why having a combined setup where you can couple QENS and Raman simultaneously would be super nice. And we built such a setup recently, where we have this humidity chamber. So we have control over humidity and also temperature. Neutrons would enter here. We have a Raman window for Raman measurements. The entire setup would look like this. We have here a connection to a thermal bath for temperature control, and a connection to a gas flow system who guides nitrogen with a certain humidity through the chamber. The entire chamber looks like this. This was last November at PSI, where we commissioned the entire setup. These would be our QENS data. This would be the corresponding Raman measurements. Worked actually quite well. We recently had a second beam time with an improved setup. It's really nice. So if this would be of interest to any of you, please send me a message or talk to me for sure. So this setup is there to be used also by external users. We submitted it to Journal of Applied Crystallography. I already did the revision, so there's hope that it will appear soon. So that you can get more infos and details about this. And with this, I'm at the end of this talk. I want to thank a lot of people. So a lot of beam times, a lot of local contacts, a lot of facilities. BMBF funded most of it. And of course, you, thank you for your attention.